Hey everybody, this is Dr. Jacobs. Welcome back. This week we're going to be learning about measures of variability. So for this unit, you'll see within our folder for this week that there is a handout. You will want to get that handout. You're going to want to download it. You're probably going to want a paper copy of it. So if you want to print it, or if you have an iPad that you can write on the worksheet and work through it. For this class, for your exams, I'm going to be seeing and testing if you understand what we're learning and critical thinking about it. So it'll be really important that you follow along and do these activities, or you're going to be very confused, not just in this unit, but all of our units build on one another. So if you don't get this now, it's going to be really, really hard for you to catch up. So make sure you download this. You can put like 3 holes in it. You can create a binder for this class. I think that'd be a really good idea. And then when we get to our calculation assignments, you'll have something to help yourself walk through it. All right, so let's get started. In this unit, there are some things I want you to be able to do before we get to the end of the unit. I want you to be able to accurately define measures of variability in your own words. I want you to be able to list the types of measures of variability. I want you to be able to accurately identify all the specific types of measures of variability based off of the provided information. So this is based off of a data set. You could tell me which ones you could do. I want you to be able to calculate the exclusive range, the inclusive range, the mean absolute deviation, variance, and standard deviation accurately. So you won't be doing these calculations on the exams, but you will be doing these in our calculation assignments. I want you to be able to explain why you must take the absolute value or squares of the deviation scores in order to calculate various measures of variability. I want you to be able to explain the relationship between variance and standard deviation. I want you to be able to use the phrase unbiased estimate and explain why the sample and population formulas for variance and standard deviation are different from one another. And then I want you to be able to explain the strengths and weaknesses of each measure of variability that we learn about. All right, so when you hear the word variability, what do you think about? Pause me, think about it, verbalize your answer. This is how you're going to practice. It's really hard in an online class for me to be able to guide you. So you got to listen to me. You got to pause this, think about it. When you hear the word variability, what do you think? So if we look at the Merriam-Webster definition for this word, it means able or apt to vary or subject to variation or changes. And so when we think about measures of variability, what we're trying to do is try to get an idea of how our data set varies from itself, and try to have a number or numbers that help us represent how it varies. Okay, so another definition is characterized by variations or differences. Because if I were to ask our entire class right now, how many times have you gone to Disney World? Not everyone's going to have the same answer. I went once when I was 7 years old. I don't know what y'all have done, but there's probably a lot of variation in this. Maybe somebody goes every year. Maybe people have never been, but our answers are probably not going to be exactly the same. So practically, when we're doing these measures of variability, we're seeing how scattered or varied our data set is. So now that we're thinking about some of those unit learning objectives, how would you define measures of variability in your own words? All right, so there are a bunch of different names. I did not make up all these different names. Statisticians can be a little tricky. Like I am trained as a psychologist, not technically, my PhD is not in stats, even though I use them and wrote this book about them. But statisticians come up with tons of names for the same thing. It's very frustrating. But the reason why I'm telling you these different ones is you may hear them or read them in a different way than what I'm using measures of variability. Sometimes they are called measures of dispersion because if something's dispersed, like perfume disperses in a room, it spreads out, right? There's some variability. Sometimes you hear them called as measures of spread. So we have all these different names for the same thing. There's potentially more that I haven't heard of yet. And as I hear more, I'll add them in. So interpreting symbols are going to be pretty important for us to interpret. Sometimes our symbols are going to have some subscripts. And so anytime that we have a symbol and it has a subscript, it's saying something about the larger symbol. So for example, right now, and this will actually be apt to change later, the symbol X represents data in our sample, not that symbol, that will stay the same, but sometimes we'll see X sub 1, and we know that that 1 is telling something to you about the larger symbol, okay? So for example, right now, if we have an X sub 1, we're just saying the data for participant 1. That will change later on when we have more than one X value, but that is future S problem. All right, so measures of variability. This is a number or numbers that describe how spread out the data set is. Again, measures of variability. This is a number or numbers that describe how spread out the data set is. I'm going to teach you some in this class. There are other ones that I am not teaching you, and you can learn later in different classes and things like that. The ones that I'm teaching you in this unit are ones that we're going to use in this particular class that will help push forward your understanding. So if you're really struggling with understanding what we're doing here, you can always pause, rewind this video. You can always also use my office hours to ask questions. If you can't come in person, we can have a Google Meet or something like that. And if my office hours don't work, you can always send me an email and we can try to find a common time to meet as well. All right, types. So we're going to learn different types of measures of variability. We have the exclusive range. We're going to learn about the inclusive range. We're going to learn about the mean absolute deviation. We're going to learn about variance. And we're also going to learn about standard deviation. All right. So probably coming into this, if you've not been exposed to any of these measures of variability or most of them, this is the one that you've most likely been exposed to already, the range. And this is actually the simplest form of variability. It also provides the least amount of information. So again, the range is the simplest measure of variability, and it gives us the least amount of information. But it's also the easiest to understand. So strengths, it's easy to understand. It's not hard to calculate. Some weaknesses of this is that it doesn't give us a whole lot of information. Something else that's interesting, there's no commonly accepted symbol for range. So for this class, typically what I'll do is if I want to identify which type of range it is, I'll usually write out the word range and then put a sub symbol. For the inclusive range, I'll usually put INCL. For the exclusive range, I'll usually put range and then lowercase like EXL or EXCL. You could even do range sub EX because there's no commonly accepted symbol for range. So the exclusive range, if you see here, I have range sub EXC. That's probably what I'll use most frequently to refer to exclusive range. And to do this, we see that we just take the maximum value in our data set and we subtract the minimum value. When we hear the word exclusive, what do you think? So if you are in an exclusive relationship, what does that mean? It means you are only seeing that one partner. You are only dating that one partner. So exclusive means that we don't include everyone. We're just very exclusive. If you're at an exclusive club, they only let certain people into that club. And so when we think about that, that helps me remember that it's just the maximum value minus the minimum value because we're very exclusive. We're not including everyone. Okay, so if I wanted to write this out in symbols, I put range sub EXC equals X sub max. So that's saying the maximum value of X minus X sub min, which is saying the minimum X value in your data set. So you'll want to go ahead and go put these on your symbol sheet if you have not done that so far. All of these are fair game for our exam. All right, so then the inclusive range. When we hear the word inclusive, what's that mean? We include everybody, right? And so if you go to an all-inclusive resort, they provide your food, your entertainment, your drinks. They include everything in your one price, right? We include everyone. And so when we're looking at this type of range, we have range sub INCL. So that can be our symbol for inclusive range. And that is where we take our maximum value minus our minimum value. And then we add 1 because we want to include everyone. So inclusive range, we're going to use especially later on when we get into the next unit, when we're building like histograms and frequency distribution tables, we'll use this to be able to calculate something else. So it's really important that we're able to use this. Also, have you ever had that problem like how many days does this thing include, and or how many values does this include? If we just do the exclusive range, a lot of times we'll leave out one of those values, and we'll really work that out in our next unit when we use this practically. So for all you need to know right now, to calculate the inclusive range, you take the max value minus the minimum value plus 1. So we put that into symbols. We have range sub INCL equals X sub max minus X sub min plus 1. So that's saying the inclusive range equals the maximum value of X minus the minimum value of X plus 1. So now that we've gotten through the 2 different types of range that we'll learn in this class, I like to use this tree as an analogy for teaching how to calculate the mean absolute deviation, the standard deviation, and variance. And so this tree here is called the bur oak tree. I don't know if y'all have visited Columbia, Missouri. I think technically this tree is in McBain, Missouri, but a lot of times it's affiliated with Columbia, Missouri, because that's a bigger town. It takes like 7 or more grown people holding hands around that trunk of that tree to be able to go around the circumference of that trunk. This is a very massive tree. If I was standing next to that tree, I would be very, 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 very tiny. It's my favorite tree in the whole world. So I like to use this tree because it is massive. It takes up the whole sky. And it's a really great metaphor for learning some of the measures of variability that we're going to do. And so if you imagine this big tree, what we're trying to accomplish, or the goal that we're trying to accomplish with the mean absolute deviation, variance, and standard deviation, is people wanted to be able to figure out, okay, how much or what is the average distance each of our x's scatter around our mean. Okay, so that was the goal. So when we're looking at this tree, if we can imagine the trunk of the tree or the center, that is our mean. And then we can imagine each of our x's, each of our data points scatter around and are at the tips of the branches, right? And so what they're wanting to do is try to figure out how far each of our data points fall away from this mean, and then find the average of those differences. And that's a really hard thing to think about, right? So we're essentially trying to find that. I'm going to use average, even though it means basically the same thing, and to describe it so that we don't get confused between the two. They're trying to find the average distance each of our x's, our individual x's, fall away from our mean. Okay, so remember this goal, because what we're going to do is we're going to work through an example, and you're actually going to kind of calculate these formulas on your own just from knowing what we're trying to accomplish. Okay, so make sure you're doing this actively, and doing this the way that I'm teaching you through this lesson. That way it will make sense for you what we're trying to do, because this process will be very concrete and this will become more abstract. So if we can use this example and walk through this, and you do this honestly, you will understand this, and this will be really great for your understanding of statistics. Okay, so rounding reminder, because we will be rounding numbers, we always go to 2 places past the decimal unless I tell you otherwise in this class. And this will be very important, and we will do that in each step. You cannot just put your numbers into a calculator. This is not a plug and chug type class. This is an understanding and critical thinking class. So make sure that you're doing this for each step so that you don't get lost. Okay, so let's practice this. If you get the number 2.405, what would you round that to? Pause this video, figure it out before you move on and hear me say what we're doing next. What would we round 2.405 to in this class? If you said 2.41, absolutely. We know that when the 3rd place past the decimal is 5 or above, we are going to round up. If it is below, if the third place past the decimal is below 5, we keep the number the same. All right, so then let's look at this, practice number 2. What if the number was 3.694? What would we round that to? If you said 3.69, you are correct. Remember, if the third place past the decimal is underneath 5, we keep the place 2 passes the decimal the same. All right, practice 3. What would we round 1.599 to? What would we round this number to? It's a little tricky. That's why we're doing it. If you said we round it to 1.60, you're correct. So here we see that 3 places past the decimal rounds up the second place past the decimal, which is already a 9. So that moves it to 1.60. So we want to make sure that we're rounding correctly. Every semester, I remind students this is how we're rounding. And then we have rounding errors, and then the numbers are off a little bit. So we want to make sure that we round each step to 2 places past the decimal. So some housekeeping. In the handout that I gave you, we have tables. Make sure you're using these tables to do all of your calculations. This will make things easier for us. If you don't use the tables on the calculation assignment, you're likely to lose points because it'll make it very hard for me to grade, and it'll also make it really hard for you to organize this information in your head. And so we want to make sure that we're taking this process slow, that we're keeping all of our work organized, that we are showing every step to our work, and that way we can stay together. So we're going to learn about the 3 next measures of variability together, that mean absolute deviation, standard deviation, and variance, because the process is very similar up to a certain part for each of these. So we're going to problem solve a little bit. The first 2 steps for mean absolute deviation, standard deviation, and variance are all the same. Step 3 and beyond is where they differ. All right, so let's do some guided understanding. Let's say we wanted to find the mean absolute deviation, variance, and standard deviation of this data set. So we see we have 5 different participants. They told us how many live shows they went to last month. And so we have our little data set here. If you look on our worksheet, if you look up at the top of the data set, this data set is reflected in your worksheet here. All right, so let's continue. Okay, so if we were wanting to find the average distance each of these individual x's are away from the mean of our data set, what is our first step? What do we have to do very first? So if we want to find the average distance each of these x's are away from the mean, what do we have to do first? Pause me until you have an answer. Don't continue this video until you know. Don't write the answer in the comments section. Just pause it and answer out loud for yourself. If you said the very first thing we have to do in order to find the average distance each of these x's are away from the mean of the data set is find the mean of our data set, you are absolutely correct. So what I want you to do right now is go to your handy dandy worksheet. We do have a place here for you to find the exclusive range and the inclusive range. You can also go ahead and do that now. So let's actually, you can do that. And then what you need to do is by your data set, we need to find the mean. What was our symbol for sample mean again? If you said X bar, you are correct. So you'll see here on my worksheet, I'm going to go ahead and write X bar. I'm going to go ahead and write our formula. We remember which is the summation of X divided by sample size, which our symbol for sample size is lowercase n. So I'm writing out each of my steps. And so go ahead and pause this video and continue doing what you're doing. Once you get that mean, come back and check your answer. All right, so we know that when we're calculating our mean, hopefully you've done this already, so I can walk you through. Our first step is that we have to add up all of our x's in our data set. So here we see we have 2 plus 2 plus 0 plus 1 plus 1. So 2 plus 2 is 4, plus 0 is still 4, plus 1 is 5, plus 1 is 6. So we have the summation of x, or 6, divided by our sample size. We see we have 5 participants here, so divided by 5. All right, so we have our X bar equals the summation of X divided by lowercase italicized n, which is our sample size. We see that our summation of X's is 6. and then we took 6 divided by 5. And we see here that when we take 6 divided by 5, we get 1.20. We see that we're taking it to 2 places past the decimal. We're writing it on our sheet so that we can work through this one by one, because this is for your notes. These are for you. All right, so if we're wanting to find the average distance, each of our x's are away from the mean. We just found our mean. What do we need to do next? So if we need to know to find how far the average distance each of these x's are away from the mean, what do we have to do next? So really think about it. Do not continue in this video until you say this out loud. Don't write a comment about that right there in our lecture. Just go ahead and think about it and then check your answer with me. Okay, so if you said that in order to find the average distance each of these x's are away from the mean, then we need to figure out how far each individual x is away from the mean. You are absolutely correct. And those are called deviation scores. So the next thing that we're going to have to do is figure out how far each of our x's are away from the mean. We call this a deviation score, and you're absolutely right. So here we're going to take each individual x in our data set. So if we look at this mean absolute deviation table, we see that we have our x's here. In the next column here, we're actually going to label the column x minus x bar. That's actually the formula for our deviation score. So hopefully you can see that there. So we have our ID number, which just tells us which participant it is. Then we have our x values. And then the next column, we're going to calculate our deviation scores, which is just our x minus our mean. All right, so these are called deviation scores. The symbol for deviation scores is capital italicized D. We actually will see this symbol for something else in the future as well. But for right now, put capital italicized D equals deviation scores in your handy dandy symbol sheet. So pause me right now and go quickly to your symbol sheet and write D equals deviation scores there. All right, so again, I already told you the formula for this. You could technically label the second column capital italicized D. I rather put the formula now because the formula tells you exactly what you're going to have to do. You're going to have to take each of these individual x's minus the mean and put that value in that column. Okay, so our formula for our deviation scores is each individual x minus our data set's mean. Okay, so we're going to go ahead and calculate these deviation scores. Go ahead and use the mean absolute deviation table right now. Like I said, when we're calculating the mean absolute deviation, variance, and standard deviation, these steps are all the same so far. The next step will change a little bit depending on which one we're trying to calculate. But for now, you can go ahead and calculate these deviation scores in the second column here. And actually, when we get onto the other page, when we get into standard deviation and variance, which follows more steps together, you'll actually write your deviation scores in the second column as well. And they'll be exactly the same because these two steps are the same at first. So if you want to do that after you calculate them, you can write the deviation scores in here too, because they're going to be exactly the same. All right, so go ahead and calculate your deviation scores now. So let me help you with row 1 or participant 1. So if we see where ID 1 is, we see that our X is 2. So in that first column there, we have 2 minus 1.20 equals, you see here. So you got to make sure that you're writing out all of your work. 2 minus 1.20 equals, and that will be your deviation score. So go ahead and calculate all of your deviation scores right now. You can pause me while you do this, remembering we're rounding to 2 places past the decimal. You will have to do this for each row in your worksheet, and you're going to want to make sure that you show all of your work. You're also going to want to make sure that you're very mindful of your negative symbols so that when we have negative numbers, that you have those numbers placed accurately, because sometimes negative symbols are really easy to lose track of. You're just going to want to make sure that you can see them very well. So go ahead and do that. Pause me right now. I'm actually doing this right now while we work. I need to go turn my office light back on. It comes off every 20 minutes. But since I'm having to show you this paper, it's not a very good idea for me to leave my light off. That way you can see what we're doing. So go ahead and calculate this now. Pause me and then come back after you've done this on your own. All right. So when we go through and show all of our work, we see that our deviation score is 0.80 for the first participant. The second participant had the same score, so it makes sense. Their X value is 0.80 away from the mean. So when we do 2 minus 1.20, we get 0.80. In our third row, we have 0 minus 1.20 equals negative 1.20. Then we have 1 minus 1.20 equals negative 0.20. And then when we get to row 5, we have the same thing. So we have 1 minus 1.20. So now that we have that, I'm going to scoot back for a minute because I want to ask you a question. So now that we have all of our deviation scores here, if we wanted to find the average deviation score, which is the goal of mean absolute deviation, variance, and standard deviation, what would we do with these numbers if we found the average deviation score? If you said we would add up all these numbers and divide by the number of participants, you're absolutely correct. Okay, so let's go through and do that. If we add all of our deviation scores, so below here where we have this extra box, I'm going to write the summation of open parentheses x minus x bar close parentheses equal. So let me write that out and then let me show you what that looks like. Okay, so we remember that the summation symbol is telling us to do everything that follows this. We know with order of operations that we got to do our parentheses first before we follow our summation symbol. So we go through and add all of these up. What number do we get here? Okay, so do that math, pause me, and then we'll come back together. Okay, so right now you might be like, well, crap. I got 0. If you got 0, you are absolutely 100% correct. And this is very frustrating, but also very exciting because this is going to be the explanation of why we have to do certain things to do mean absolute deviation and variance and standard deviation. So when we're looking at that, what caused some of our deviation scores to equal 0, right? Because if we were to continue to try to find the average deviation score and we took 0 divided by 5, that number would still be 0. And that does not represent about how far each of these values are away from the mean, right? So if we have those positive numbers, that just means that those x's are to the right of the mean. Negative numbers just mean that those numbers are just to the left of the mean. And so when we're looking at that, why did we get the summation of our deviation scores equal 0? So look at your data set, look really hard, think about this before you move on. This is going to be critical to your understanding of this, okay? So look at it, think about it, pause me, don't write a comment about this. Use this for yourself. Think about this for yourself, so pause it. If you said it's because we have positive and negatives, you are 100% correct. Here we have positive and negative numbers, and that's problematic because when we're looking at standard deviation, variance, and mean absolute deviation, the mean is always in the absolute center of our data set. Our data points are always balanced around it. So that number will always equal 0. If it doesn't, if the summation of your deviation scores doesn't equal 0, that means you did something wrong, okay? But this is problematic because that does not help us figure out what the average deviation score is. That's very problematic. And so the researchers then realized that, well, crud, what do we do now, right? So if our goal is to get close to what the average deviation score is, what could we do mathematically? What kind of mathematical operators? So mathematical operators are things like plus, minus, multiplication, division, squaring, square rooting, all these different types of things. And there's going to be two answers for this. What mathematical operator, what could we do to those deviation scores so that we don't change their proportions where, like with the relations to one another, but make it so that they're all positive. So pause this. Don't spoil this in the comments for everyone. Think about this for yourself. What could we do to every single one of our deviation scores? So what we do to one deviation score, we have to do to all of them. That won't change the proportion. That will allow us to turn all of them positive. There are two different things that we can do. So make sure you've come up with your answer before you move on, because this is very critical. There are two different mathematical operators that we could use. One of them, some of you have probably forgotten about because you haven't done for a really long time. Literally, we could just take the absolute value of each of our deviation scores. So if we do that, if we decide to take the absolute value of each of these, because that still keeps the size the same, pluses and minuses with our deviation scores just says if it's to the left or right of our mean. So we can put our absolute value bars. If we do that, all we do then is we take our numbers in that third column there, and we just turn all of them positive. This was the goal of doing these types of measures of variability. And this is actually the easiest way to do it. So if you see here, I went and took the absolute value of each of those. And that's on the path to do mean absolute deviation. What is the other way that we could do? What is the other thing that we could have done instead? If you said out loud, you could multiply each of them by -1. That's not correct, right? Because if that would change our negative numbers to positive, but then all the positive numbers would turn negative. Sometimes that's something students will say. What could you do though? If you say you could square each of your deviation scores, that's absolutely correct. When we square a number, a negative number, it becomes positive. It also keeps the proportions the same when we square. And so if we went and squared those deviation scores instead of taking the absolute value, we would actually be on the path to calculate variance and standard deviation instead. All right, so here we see in step 2, when we add up all of our deviation scores, that it equals 0. The only time that number won't equal 0 is if we rounded somewhere. So like if we rounded our mean, or we rounded these deviation scores because the numbers came out weird, then it usually would be only slightly off of 0. All right, so when we're looking at this again, I plotted these numbers onto a number line to help visualize it here. So let me talk us through what's going on here. We see that our mean here is in the middle, here. So you see 1.20 on our number line, that's the mean. Okay, when we're finding these deviation scores, we see that x1, if we look in our data set, x1 was 2. So if we look on our number line, that's where we have x1. And so what this deviation score is telling us is how far is x1 from our mean, which is our 1.20. We see that it's a positive number, which means that 2 is just 0.80 to the right of the mean. We see with our second deviation score, that's the same thing. Because x sub 2 was also 2. When we get to our third x, our third participant's x, we see that our x was 0. So we see that 0 is 1.20 to the left of our mean. And so if we look at this number line, we can see that our deviation score is -1.20. That negative, again, is just telling us that our x is to the left of the mean when we plot it out. When we get to our fourth score, which was a 1, we see that 1 is 0.20 to the left of our mean. And we see the same thing with our fifth x here, that we see that 1 is 0.20 to the left of the mean. And so what they're trying to do again with mean absolute deviation, variance, and standard deviation is see what's the average of our deviation scores. Because when we add up all of our deviation scores, they equal 0. They had to do some finagling. So some scientists decided they want to do mean absolute deviation. And to fix that, they just took the absolute value of all the values, all of our deviation scores. And then if then they could use that number to find the average distance each of our x's are away from the mean, because remembering positive and negative is just telling us what side of the mean our number is on. All right. So again, when we add those deviation scores, we see that they equal 0, which is problematic. So again, we have two solutions for the summation of our deviation scores. We could take the absolute value of our deviation scores and then add them up, and then divide by our sample size. This is called our mean absolute deviation. Our symbol for this is going to be capital M-A-D, MAD. And this is really interesting because this really isn't taught a whole lot. Not a lot of people know what the mean absolute deviation is, but it's actually the one that makes the sense. This actually is the average distance of our x's are away from the mean. But they both MAD and what we'll learn as standard deviation both came popular at the same time, and standard deviation just happened to be the one that got more popularity. All right. So the other way we could have done it was square each of our deviation scores, then add them up together before dividing by our sample size to find the mean of those. All right. This is how you go to continue on to calculate both variance and standard deviation. All right. So let's continue with step 3 of the mean absolute deviation. So we're working through this table on the front. We already have our deviation scores showing all of our work. We see that we're showing each step. So we've went ahead, hopefully, and did the deviation scores. Hopefully you found the absolute value of each of your deviation scores. If not, go ahead and do that right now. Okay, so when we found our absolute values of our deviation scores, those are the numbers that I have on my worksheet. Okay, so now if we wanted to know our average absolute value of our deviation scores, how would we find the average? What would we do? If you said we need to add up all of the numbers in our 4th column and divide by our sample size, which is 5, that's correct. And that will actually get us our mean absolute deviation. All right. So to do this, we find the mean of the absolute values of our deviation scores. And when we do that, we find that we have our sum of our absolute value of deviation scores equals 3.20. Make sure you're working through this. And then our last step to finding our mean absolute deviation is to divide that sum by the number of our participants in our sample. So we have MAD equals the summation of the absolute value of x minus x bar divided by n. So this is going to be our formula here. And so here, then you go ahead and write your next step. We found that when we added up all of our absolute values of our deviation scores, we had 3.20. We see that we have a sample size of 5, so n equals 5. So remember, we're writing out each of our steps when we're showing our work, just like this. And then let me pull up a calculator real quick. Then when we take 3.20, make sure you're doing these before I tell you the answer. When we take 3.20 divided by 5, we get 0.64. So let me get rid of my calculator real quick. Okay. We get that our MAD equals 0.64. And so that actually is the average distance each of our x's are away from the mean. And so this is not the popular one, unfortunately. I kind of wish that science would have used that one because it makes a lot more sense. But what we're going to use, the reason why I'm teaching you mean absolute deviation, even though other people don't teach it anymore, is this gives us a really good idea of what variance and standard deviation mean. Okay, so when we're going through on our next page, because we'll flip over and do our variance and standard deviation now, it'll help you really understand what those mean. So if you don't understand mean absolute deviation, you can rewind the video, walk through this again as many times as you want. You can also, after you've watched this, if you still have questions, you can write questions. Just don't write the answers to the things that I'm asking you for you to practice your learning so other people can practice their learning too. You can ask questions in our lecture, and you can also come into office hours. All right, so the steps to calculating our mean absolute deviation: you calculate the mean of your data set. You take each x minus the mean to find our deviation scores for every x. You take the absolute value for each of our deviation scores, and then you find the mean absolute value of those, or you find the mean of the absolute value of our deviation scores. That's exactly what you need to do. Okay, so again, if we're going to define this, the mean absolute deviation is the mean distance your x's are away from the mean. All right, so that moves us on to our variance and standard deviation. So on our second sheet, hopefully you printed on one page. My printer didn't let me. We have our tables for our variance and standard deviation. You're going to want to make sure that when I ask you questions that you're working ahead, that you're doing these calculations and writing them down. That way you know how to do this when I require you to do it in our calculation assignments. Okay, so the process is the same. And I told you all that, you know, if we want to find the average distance each of our x's are away from the mean, the very first step is that we have to find that mean, which we did, right? So we wanted to go through the steps again. We would look at this and we see all of our x's. We would take our summation of x, right? So if we have the summation of x, that's telling us to add up all our x's. We have 2 plus 2 plus 1 plus 1. Summation of our x's is 6. Then if we wanted to find the mean of this data set, we would have x bar, which is our symbol for sample mean, equals the summation of x divided by sample size, which is lowercase n. See, I'm writing out each of my steps individually. Hopefully you are doing the same thing. So we see that 6 divided by our sample size of 5, and we write out that step. Remember, we're writing out each step, and we find that that number equals 1.20. So our first step was to find the mean. We found that our mean equals 1.20. Our next step, if we're trying to find the average distance each of our x's are away from the mean, we have to find what that distance is. We have to find how far away each of our x's are away from the mean. That's also called our deviation score. So our third column there, we have x minus x bar, and then we're going to find that for each of those. You've already done this work when we did the mean absolute deviation. So either you can just copy from your first page or you can keep practicing, right? Practice is a good thing. So when we go through and do this, we see for our first deviation score that we're going to take 2 minus 1.20. And we see that our first x is 0.80 to the right of the mean. And we're going to carry that through and do all of the deviation scores for each of our numbers. And so I'm sitting here doing that real quick. You can pause me so that you can take as much time as you need to complete this task. It's really important that we keep practicing this because even though we're learning this to learn standard deviation, this actually is going to follow us all the way through and is going to haunt our dreams for the rest of the semester. So this is something that you're going to really want to do. All right, so we remember the goal of variance and standard deviation was to try to figure out what the average deviation score was. We found out when we remember that when we add up all of our deviation scores, that number, as long as we've done our math correctly and we haven't done any rounding, will always equal 0. That was problematic. So for variance and standard deviation, we know that we're going to go through and square each of those deviation scores. All right, and that's what we're going to label in this last column here. We're going to have x minus x bar squared. And so we will use that. So that's where we differ from our mean absolute deviation. Okay, so again, rather than take the absolute value of each of the deviation scores like we did for the mean absolute deviation, both variance and standard deviation square the deviation scores to eliminate the negative scores. Okay, so both take the sum of the squared deviation scores. So that is a mistake in our PowerPoint. So let me fix that real quick. Let me fix this of the squared deviation scores, and that number is called our sum of squares. So let me get back onto our current slide, and then let me share my screen again because it stopped sharing with you once I did that, I think. I am terrified that this is not going to work now. So I'm going to say from current slide, hopefully my Zoom will show back up. Let's try to use some functions. Okay, there we go. We're just going to try to share this. Hopefully this will work. Current slide. All right, here we are. Hopefully it's showing you this. If not, I'll be very sad. All right, so variance and standard deviation again. So instead of taking the absolute value, we squared each of our deviation scores. When we add up, after we find each of the squared deviation scores, when we add those up here, we call that our sum of squares. So go ahead right now, go through and do all the math for this. So in this column, you'll see for our first squared deviation score, I'm going to take 0.80 and I'm going to square it and I'm going to get our number. So if I do that in the calculator, I see that if we square 0.80, that number is 0.64. You'll see here that we always are going to show all of our work. You should show every step. That's how you'll get credit for it. And do that for every single one of our deviation scores. So you're going to square every single of those, all of them. Remember, when we're dealing with negative numbers, like we are in the last three participants, that when you square a negative number, that becomes positive. Okay, so we got to remember that all of our numbers, when we square them, all of them should be positive. If not, that means you've done something wrong, and you're going to be very sad. So the way that I like to keep track of that a little bit is I like to use parentheses around, especially my negative numbers, but I actually do it for all of my numbers because that helps me keep track of, especially when I end up having negative numbers. All right, go ahead and do all of those squares and then we'll continue. So if we remember, this is where variance and standard deviation are going to differ from mean absolute deviation. All right, so step 3, again, for variance and standard deviation, you're going to square those deviation scores. That's what we're already working on. And when you go through and do it, those are going to be your answers. So make sure you check your answers real quick. Now, the tricky thing is, if we wanted to find the average of those squared deviation scores, what would we have to do? If you said we have to add up all of our squared deviations, you're 100% correct, and that is going to be our next step. That number is what I was talking about, is our sum of squares. Our symbol for sum of squares is going to be SS. Usually I'll just write the formula when I'm writing it in my table, but you do need to know that symbol. I think it's the worst symbol ever. But if you look in your table, I have SS equals the summation of open parentheses x minus x bar, close parentheses squared, and then you're going to add all those up to get your sum of squares. Okay. So that's our next step. And when we do that, we find that our sum of squares equals 2.80. So when we wanted to take the average, right, of those square deviation scores, we know that we have to add up all of our square deviation scores. And then what's our last step? If you said our last step is to divide our squared deviation scores by the sample size, you are correct. And so actually our formula for variance is our sum of squares divided by our sample size, and that will give us our variance. All right, so when we go through and walk through all these steps, we see that it can be a little scary, right? Sometimes people forget that that numerator of our variance formula we actually did in our table, and that you just have to take that number over and move it to the numerator of our formula. Remember, that's exactly what you got to do, divide it by 5. And then when we work this out, we take 2.80 divided by 5, and we see we get 0.56 as our answer for variance. So the thing is does that actually represent how far each of our x's are away from the mean? If you said no, you are correct. The variance doesn't actually do our job. Why doesn't it actually do the job that we originally set out to do? If you said it's because we squared our deviation scores, you're absolutely correct. And so, although this is how we get at the variance, we need one more step to find our standard deviation. So if we wanted to try to take back all that squaring we did when we squared our deviation scores, what's the opposite of squaring something? Pause me till you have an answer. Don't write it in the comments, just shout it out loud. If you said take the square root, you're absolutely correct. And so in order to find the standard deviation, what we would do then is take the square root of the variance. And what that does is try to put it back in the same form that we had before we did all of that squaring. Okay. So if we're going to define the variance is technically the mean of the square deviation scores. Now, if I would have said that in the very beginning, that would make no sense, but we walk through it. We know that's true. That's still a little fuzzy, and the understanding of it will get better over time. That's very tricky in some ways. But if you think about everything we just did, that will make sense. We literally took the mean of those square deviation scores that we had. Why is this a little difficult to interpret, though? It's hard to interpret because we squared those individual deviation scores, because when we added up the deviation scores before, the positive and negatives made it equal 0, and we couldn't do anything with that number. And so because we squared those individual deviation scores, it makes it really hard to interpret. And that's why that one, I think, is the hardest to understand out of all of our measures of variability that we're learning. All right. So again, if we wanted to get that number, our variance number, to get back into standard form, close to the data we originally worked with, we would do what we already talked about. We would take that square root of the variance. The thing is, have you ever said something to somebody that you wish you could take back, but you couldn't? That's kind of what happens with standard deviation. Although we're taking the square root at the end, we're not actually taking away everything that we did to those numbers. It's about approximate, but the numbers aren't exactly the same, okay? But when we do that, we do get that standard deviation. So our last step to find standard deviation, we just take the square root of the variance. So if you do that, you can work that out before I show you the answer. Go ahead and pause me. We see then our standard deviation is approximately 0.75. All right, so then if we look at the relationship between standard deviation and variance, our standard deviation always is going to equal that square root of our variance. And this is a relationship that you need to remember, right? So our standard deviation equals the square root of the variance. So they're very close. You actually calculate one on the way to the other. And so you will understand that. So where are the symbols then? So at this point, you're probably wondering, why haven't I given you the symbols for variance and standard deviation? The reason why I haven't done that yet, I wanted you to conceptually understand what variance and standard deviation are first. If you don't understand that, pause this now, rewind it, and then I'm going to make it a little bit more complicated. Okay, so I'll give you the symbols first, but I'm not going to give you the formulas for variance and standard deviation quite yet. All right, symbol time. So you'll see we have a lowercase sigma squared is the variance of a population. Lowercase sigma is the standard deviation of a population. S squared is variance of a sample. And then S is the standard deviation of a sample. So go ahead and write these symbols on your symbol sheet. You can pause this and do that. So a lot of times students struggle with some of these symbols, especially for variance, because it's just the squared symbol for standard deviation. If we remember back to the other page, our previous slide, or 2 slides ago, I guess, that's because our standard deviation equals the square root of the variance. Okay. And so when we look at our symbols then, that relationship is showing through in these symbols. Okay, it's really important just to memorize that the symbol for variance is just the square deviation symbol, and that you don't have anything else that you have to do. Sometimes students really struggle with that, and that messes them up when they go to do their calculations. All right. Sometimes, because again, the variance symbols look funny, students can be tempted to try to do additional unnecessary steps when they're doing these calculations. All right, so here are our formulas for populations, for variance and standard deviation of population. Pause me and look through these. Okay, so what about the sample formulas then? So you'll notice I've been hiding the formulas for the sample variance and sample population now, and we'll talk about why. Gasp, why would I do such a thing? So the formulas for variance and standard deviation are different depending on whether you're calculating them for a sample or a population. Okay, so let's think about this on the next slide, critical thinking. What happens when you make the denominator of a fraction smaller? Okay, so you can work this out. If you have 2 over 2 equals, and then we have 2 over 2 minus 1. Do those on your paper and see what happens. So what happens when you make the denominator of a fraction smaller? So what would happen then if we made if it makes the number get bigger, right? So what happens to standard deviation when you make the denominator smaller? If you said it's going to make that standard deviation bigger, you're absolutely correct. It makes the standard deviation larger. Okay, so why would the standard deviation of population be larger than the standard deviation of a sample from that population, right? Because what happens in the sample formula, we're going to actually take n minus 1 in the denominator so that we can make the sample standard deviation variance arbitrarily, artificially, I guess is a better word, larger. Why would we do that? If you said because in an overall population, there's actually probably more variation than you would see in a sample, that's 100% what we would do. So they call this an unbiased estimate when we put n minus 1 in the denominator. And the reason that we do this is so that our sample variance, our sample standard deviation more accurately represent the population that we took our sample from. Okay, so research has shown that when calculating these with a sample, if you have n minus 1 in the denominator, it's much closer to the population standard deviation than if you don't. And they call that the unbiased estimate. Okay, so here are formulas for the samples for variance of a sample and standard deviation of a sample. You'll want to look at these and review them. And this is why symbols are really important to learn. Okay, and that is it for this week. This is a lot. Make sure you take your time with this. You guys are going to do great.